Uh, the Pakistan nuclear program was started back in 1950s when the first nuclear power plant in Karachi, Kanap 1, was set up. But later on, like in other years, the more main focus was not towards the power generation from the nuclear energy, but towards the weaponization or the nuclear weapon programs. But back in 2000, uh, the shift was back to the nuclear power, and which was nuclear power plants, and that was reflected in Cheshma nuclear power plants, Cheshma 1, 2, 3, and 4. Then in current years, the Pakistan have also planned two biggest nuclear power plant for its country, and that is Canap 2 and Canap 3. Each is having gross electricity capacity of 1100 megawatt each. So that would be set up in Karachi, and that is called as the Karachi Nuclear Power Plant 2 and Karachi Nuclear Power Plant 3. Um, it is the Pakistan itself is producing around 13 or the installed capacity Pakistan from the nuclear is 1318 megawatt, while it is planning like after the setup of the two further nuclear power plants, it will be increased to 2028 megawatt. The nuclear share of Pakistan is around less than 7%. It's around like 6.5% nuclear share from the electricity, or the electricity generated from the nuclear energy is less than 7%. Now, going towards the nuclear energy itself, and let's compare it to with the chemical process. So that means like when let's say for example when a carbon react with oxygen, it will give us as carbon dioxide, and we know from the our previous knowledge the formation of carbon dioxide would release a large amount of enthalpy of formation of carbon dioxide in terms of exothermic or in terms of heat. Uh, in if we compare this example with the nuclear or in terms of nuclear, so that is like when carbon would react with oxygen, it will release 4 electron volt. An electron volt is equal to, or 1 electron volt is equal to 1.6 into 10 power minus 19 joule, or that is equal to 1.519 into 10 power minus 22 BTU, which give us at 4.4 into 10 power 23 kilowatt hour. So 1 million electron volt would be equal to 10 to the power 6 electron volt. So that means if I'm saying if comparing that case with the nuclear energy, so to produce 1,000 megawatt power for the whole year from the from a thermal power plant, the fission would take around 1 ton of uranium. The fission nuclear power plant would take around like 1 ton of uranium, while the thermal power plant, which actually utilizing coal, would take as 3 million ton of coal. So you can imagine like 1:3 million ton of coal is equivalent of the nuclear energy. So that's why the main focus is to have a nuclear power plant. The main focus is to capture this amount of energy and utilize it in terms of heat, and utilize it to produce the steam, and then obviously to run the turbine from that one. And what is actually a nuclear reaction? In nuclear reaction, neutron play an important role. The neutron itself is comprised of different quarks. They are subnuclear particle, we call it. These one of these carries positive charge, which we call as a up quark, and which is 1/2 of as large as proton, while the other one carries negative charge, which we call it as a down quark, which is equal to 1/3 of the charge of the electron. The neutron, which is a we call it as a neutral electrical charge, is comprised of two down quark and one up quark, while the proton, which we call it as the positive charge, positive one charge, is comprised of two up quark and one down quark. There is a close relationship between the neutron and the nucleus of the ordinary hydrogen atom. The neutron, which has got a mass slightly larger than the proton, and it when it's subjected to like a or nuclear reaction, the proton or when it the neutron is subjected to nuclear reaction, it converts to proton when it releases its down quark. Uh, when it releases down quark, actually the neutron is converted to positively charged and by releasing one negative charge particle. Uh, in this process, which is actually having extremely low mass and difficult to detect, uh, a neutrino is released, and the net result, which is actually a radioactive decay, is actually making the neutron, which is converted to a proton by releasing a particle, which we call it as a neutrino. But the process is not as simple as it look like. The cork, when they have got some interesting properties. Like when you are actually pulling them together, pulling them apart, they would be actually getting closer, harder and harder. So as a result, one quark in a proton can only be separated from the other when it is replaced by another quark. For example, if a proton and neutron are put together or put next to each other, they can exchange either the up quark or the down quark. This process would help the binding the neutron and proton to form a more stable nuclei, and that like let's say if a proton and neutron is actually fused together, we call it as a deuterium nuclei. Now the deuterium nuclei is like as twice as heavy as proton. So when they replace proton in ordinary water, that we call it as a D2O or heavy water. The deuterium nuclei now can also react with another neutron to form a tritium. Uh, but the however, uh, like the deuterium itself now is a little bit more stable than the normal ordinary water, which means like it does not absorb any further neutron to its nucleus. So that's why it is actually used in the nuclear reactor as a heavy water, which actually in which the neutron absorption is minimized when we are using the hard water in it. Sorry, the heavy water in it. The neutron in tritium, it's also, if we are say like we have got a proton and then we have got two neutron. Now the tritium itself is not a stable nuclear of the hydrogen. It actually goes into a radioactive decay, and it actually the tritium has got a half-life of 12.3 years. Now if you're talking about the nuclear fission reaction or the nuclear fusion reaction, the tritium is one of the reactant in a fusion reaction, which required lowest energy to in the reaction to overcome the electrostatic repulsion. Having said, like as earlier I said, like when proton absorb or like react with the neutron to neutron, it is not as stable as the deuterium itself. So it is more likely like it will be actually having require less amount of energy to become if I would say like to decay. And this is what actually we would be using in the excitation, or if I would say like in terms of fusion reaction. But like to that's having said like to start a nuclear fusion reaction, or in terms of what we would say like to release this neutron from the nuclear of a tritium, you would need certain amount of energy, and that energy would be supplied to the nucleus of the tritium, and then when it is actually bombarded, or when the energy is supplied to the nucleus, it will release large amount of energy, and obviously there will be actually a chain reaction. But to make this occur in terrestrial useful time required a temperature which is excess of 57 million degrees Celsius, uh, where each hydrogen nucleus and accompanying electron typically has as much of energy as if it has moved through a voltage of 5,000 volts. So what we can say, like when an electron or the nucleus of the hydrogen is moved at the voltage of 5,000 volts, actually it would be the energy which would be so enough that it will be actually going into the nuclear reaction. And once this reaction started, it will yield more energy per unit mass than any other nuclear reaction. And once it is started, it will form other nuclei. And when it is actually and releasing a huge amount of energy, this nuclei would react further or fuse further to make the chain reaction possible. The neutron released in such reaction have got energy which is equal to 14 mega electron volt. This leads to much more material damage per unit energy release in a per, in a particle fusion than the fission reaction, which mean like uh, it is definitely not possible to contain this amount of energy in a reactor itself. So when you want to contain this kind of energy in a nuclear reactor, nuclear reactor itself get damage, and definitely the further reaction would not be possible. So the only fusion, if I would say like the only usefulness of fusion reaction or in a nucleus process is actually in the nuclear weapon. Uh, there are like few methods that was producing temperature which exceed 57 million degrees centigrade. Uh, these basic laboratory methods on are and there's a disadvantage to nuclear weapons are like magnetic bottles. We have got it's huge and expensive, and it actually costs around like $10 billion. We have got like laser compression or frozen deuterium tritium mixture. It's still huge and required multi-billion dollars. Compression using exploding void does not work, need large power supply, and obviously need large amount of energy to continue the nuclear fusion. But obviously, there is actually quite a huge research going on in terms of nuclear power plants or nuclear fusion power plants. Um, sorry, the nuclear fission power plants is already available, but we have got more and more, like as the energy content of nuclear fusion is more than the nuclear fission. That's why the research is much more towards making the nuclear fusion possible for the nuclear reaction or nuclear reactor, so we can get more and more power from it. Uh, so the much more research is now towards the controlling the fusion experiments, and that mean like controlling in such a way that we can harness this amount of energy from the nuclear fusion reaction and utilize in terms of uh, nuclear power plants rather than nuclear weapon design. Uh, of the laboratory method, certain kind of magnetic bottle, which is actually mostly called as tokamak, they are actually much more feasible, and they have got much more um, like potential towards the nuclear energy. The other methods, other more methods that been funded by the European Union or the United States, they are actually they are having other programs as well, but primarily their research programs, they are actually moving around the tokamak technology, and there is actually one of the nuclear reactor, I would say a nuclear fusion reactor which have got the huge funding, and that is actually what we call it as a ITER, International Thermo, like, uh, sorry for that, International Thermonuclear Experimental Reactor. I hope like you just Google it and you will find huge information on the ITER. You can actually also Google some information about the new trends towards the nuclear fusion reactor. There are huge investment now going on to into the nuclear fusion technology, which is more safe towards the radioactivity as well, and it is more safe towards the having huge amount from the very small atoms. Um, Now the question would be, what is actually the physics behind this nuclear reaction? So, or the nuclear, the as I would say, like the basic was to get more stable nuclei. So, what is actually basics of this nuclear reaction? So if you're looking at this graph, so what we have got is like um, if we, the most stable nuclei in our periodic table is actually of the iron nuclei, which is somewhere over here. The iron nuclei is the most stable nuclei in the element, and that's why it actually occur in most earth. It is actually iron is occurring more in the O form. So the metal or the atoms which has got the atomic number less than iron, so they will actually try to fuse together to form more stable to nuclei and towards going towards the more average binding energy, while the atom which has got atomic number greater than the iron, it will try to release its energy or its nucleus or its neutron to go towards the more stability and to form the iron atom. So what we have got is like the atom which is having less energy or the less atomic number than the iron will actually fuse together, which we call it as a fusion, to form more stable nuclei, and the atom which is greater than the iron will actually release its nucleus or proton or neutron to get stable, and we call it as a fission reaction. And obviously in the next lecture we will be discussing about this one.